What if you had to live and work in the same room as all of your waste, including what comes out of your body?
EGS Program Chief Engineer. Verify no constraints to launch.
EGS Chief Engineer team has no constraints.
I copy that. You are clear to launch.
5, 4, 3, 2, 1, and liftoff.
Power clear. Now passing through max Q, maximum dynamic pressure.
Welcome to space.
As we plan to send humans farther into our solar system than ever before, there are a lot of challenges. And at the top of the heap is trash.
On a one-year mission, a crew of 4 will produce about 2,500 kilograms of trash.
But we don't have interstellar landfills. What we do have are super smart scientists and engineers working on converting trash into gas. So I am in the booth now with Dr. Annie Meyer and Jake Hochstadt. Annie's kind of reeling right now because she's actually very new to the title of doctor, and I love to embarrass her by talking about it. Annie and Jake, welcome.
Hello, hello.
Thanks.
And as with any great program, the Oscar project is an acronym. What does Oscar stand for, and what's the overarching goal here?
Oscar stands for Orbital Syngas Commodity Augmentation Reactor. So syngas is actually a shorter term for synthetic gas. Synthetic gas is usually a mixture of things like carbon monoxide, carbon dioxide, and methane, which are very simple, we call them permanent gases that are very small molecules that can be used as building blocks for other things, whether it be for life support or for fuel production. So we're creating this syngas and then converting commodities. So that's how we got to Oscar.
Annie, what got you really interested in trash and recycling? Did you have a really messy college roommate?
Yes, but no.
We all have a messy roommate?
No, my roommates were pretty clean, actually. They were tidy. I'd say, so it's kind of funny. I grew up in New York, and it always fascinated me how many people lived there and how much waste could be processed. We used to actually have the Atlantic Ocean is on the south shore of Long Island and Queens and the lower part of Staten Island. And when there was a big storm or, say, the Super Bowl, everybody, flushed the toilet at the same time, or a big storm, the storm wells would overflow and all the trash and wastewater would go into the ocean, and you wouldn't be allowed to go on the ocean, until it was cleared because things like needles would be washing up or hazardous stuff. So for me, I became fascinated with, wow, how do we manage all this trash, whether it's people's garbage in their house or, when you flush the toilet, where does it all go? And funny enough, my grandfather was a garbage man in the Bronx. So growing up, we heard a lot of stories of him being a garbage man in New York City. And so the history and the trash of New York actually just fascinated me. And it was crazy because I read this book where I learned we were just taking our trash, putting it on barges, and just dumping it into the ocean before things like the EPA were started in the 70s. And so I thought, wow, we're killing our Earth and our planet if we don't manage our waste properly. And guess what? That was, a long time ago, and we still haven't figured it out as a planet. So for me, when I started working at the Space Center and I heard it, I was kind of brought in on this waste conversion project. I was like, wow, this is like fate. I mean, this is just awesome. So I feel like it really meshes well with my synergy of wanting to save the planet and figure out the waste problem, but also having sustainable space travel. So that's kind of some of the history there.
Cool. And so obviously waste conversion, you mentioned that, Doctor. So I want to kind of key on that a little bit. So why is NASA so invested in trash conversion?
Okay, so no matter where we send humans, they're always going to have trash. Just like when you go camping here on Earth or you're sitting in your living room, you're probably producing trash. And on a space mission, the day-to-day trash, we call that logistical trash, which is like food packaging, their clothing after they've worn it. As much as they can, it all becomes trash. And aside from that, you also have human waste, such as fecal and urine. So no matter where we send those humans, they're going to be producing waste. That's going to take up space. It's going to have to be stored somewhere. It's going to smell. And it costs so much money. So why we really like our project is because it provides a sustainable avenue towards deep space exploration. If those astronauts are creating this large pile of trash, why not do something useful with it, like get back the useful stuff that's inside of it, like the raw materials. So
when you say raw materials, what do you mean? Because obviously, like, are you talking about like terrestrial recycling of plastics kind of a situation?
Sort of. So what we're doing, there's a lot of different ways you could process waste. You could either melt it back down and use it as 3D printing feedstock if it's plastic. But in our case, we're looking at taking the solid and making it a gas. We don't get everything into gas form. About 10% gets left behind, and that's either left over as liquids or metals that can be repurposed. So like a metal, that would be a raw material that we've recovered, and you can use for either 3D printing or shielding or something like that. And then the rest would be a gas. And the gas, you can either use it as like a fuel, or you can just vent it safely off the spacecraft. And now you've created a whole bunch of room for the astronauts to do other stuff like cool science or live happily in their confined environment.
How are we currently dealing with the trash that we're creating in space?
So right now on Space Station, the crew takes their trash and they put it into bags, depending on if it's liquid waste or dry waste. We would call it wet waste or dry waste, and they go into two different types of bags. And then those bags actually get stored in additional bags called cargo transfer bags. And once a visiting vehicle arrives, which is a vehicle that is launched from the Earth and attaches to Space Station, the astronauts then transfer all those cargo transfer bags into that visiting vehicle. And then that visiting vehicle separates from station and goes back down into Earth and burns up in the atmosphere. So all of that waste that's been accumulated for however long they've had it up there basically just burns up.
That might work okay. Obviously, it's not ideal if you're burning up trash and just wasting it, but it might work okay on the International Space Station. But when you're on a 6-month mission or a 9-month mission to Mars, you can't just be, ejecting trash somewhere in the middle of space. So you have to deal with that trash. So you either have to keep it on your transporting vehicle, take up a bunch of space, or use our trash to gas concept.
How do you quantify how much trash a human makes?
Okay, so on a 1-year mission, a crew of 4 will produce about 2,500 kilograms of trash.
2,500 kilograms is about 5,500 pounds.
Yeah, so if you converted all of the waste from a 1-year mission into, say, methane, all of that gas was getting used as fuel. The current public documentation for like taking something off the surface of the moon and bringing it back to an orbiting spacecraft, it's enough methane to provide fuel for that engine of that ascent vehicle, which is pretty significant if you think about it. I mean, you're saving fuel that has to be launched from Earth, kept cool. You can actually produce it from the astronauts' trash. So it's pretty significant if it is chosen to be used as a fuel.
So when you talk about methane gas and being produced, so we're talking about breaking down trash on a very molecular level. Is that correct?
Yeah. So the main trash is plastics, which are basically oil products. And so there are these long chain hydrocarbons. And if you think of hydrocarbons as these long chains of carbon molecules, and the stuff that we're exposing them to in our reactor are like chopping up those molecules. All those little molecules break down, and some of the smallest molecules, once you add, say, hydrogen, for example, you can get methane out of it. So that's how we chemically manipulate it in the presence of heat and different chemical compositions and pressures.
Cool. So Annie, tell me about your role on the project this year. What are you doing for this for Oscar?
She's leading us. That's what she's doing.
I guess my title is team lead, and I coordinate all of the awesome team members that we have. They're multidisciplinary, so we have everyone from Jake, who's electrical software. We have people from safety. We have people from communications. For us, a young or early career team that is moving so fast and is trying to fight bureaucracy and kind of going outside of the norms of the NASA culture or even traditional workplace culture, I'd say is very unusual around this neck of the woods.
Oscar is funded by the Early Career Initiative, or ECI. ECI is a research and technology initiative run out of NASA headquarters and is designed to do three things: develop the next generation of NASA technologists, develop exciting and innovative technologies to achieve NASA's goals, and encourage the use of innovative and agile methods and processes. That's really, really a big part of why Oscar exists today.
Yep.
So can you tell us a little bit, kind of big picture, what is the Early Career Initiative?
So the Early Career Initiative, I'm trying to think the easiest way to put this is it's mostly the core team of an ECI project or Early Career Initiative is members are within 10 years at a college. So the idea is NASA's trying to figure out new ways to approach problems, and they're trying to get the younger folks to look at a problem a little bit differently than the more traditional way.
It changed. It's 8 years.
Oh, it's 8 years?
Of working for the government. So it takes all ages, just 8 years of work experience.
So is this a project opportunity that's open to everybody?
Yeah, they're highly competed across all the centers. And so for the first round, when Jake was on it, they did 2 projects. And then for this round, they did 2 projects. So those are competed amongst the centers. And then you have to survive the center down selection and then survive the headquarters down selection. So it is not a common thing to see at NASA. But it's exciting.
Yes. So if I can also add what makes working for Annie so great, not to toot my boss's horn, but she's very technical. She's Dr. Meyer, right? So she's not only leading us, she knows what she's talking about. So she's...
Or do I?
You fake it pretty well. So it's great to have a leader that's actually in the weeds with us on the day-to-day process, helping us through, developing this project.
So Jake, what's your function on the team?
So... I guess I should have
Tutor of horn.
Dudunch. So, I wear multiple hats, I think. I have the electrical background, so I guess I've been doing more making sure our lab view and our hardware components talk with the software.
And were you all starting from scratch on this project? Is this kind of the ground floor?
I'd say we had a lot of heritage knowledge from the prior trash to gas project, but when it came to designing a waste reactor that could work in a microgravity environment, we were starting from the ground up. We went from concepts on whiteboards to designs on napkins, all the way to proper engineering schematics and paperwork that you would expect to see in a design review, all the way up to building, prototyping, and then testing. Yeah. And now we're analyzing data. So it's been kind of a full circle, which is also unusual for something to happen that fast on a project. We started in January. It's already December, and we've gone from design, development,
PBS approval.
Yeah, pressure vessel systems. And it's a high temperature, high oxygen system, which is considered hazardous. So we've had to be very careful in how we rapidly design.
So Annie, I know in the trash to gas project of the past, you all used some simulants to kind of mimic human waste. Is that correct?
Yeah, we have a recipe for poop and a recipe for urine.
And are you using those for Oscar at this point, or is that like for the future sometime?
We will be. Probably in January is when we'll start doing fecal and urine in the reactor. Why is that crazy? Everyone has waste. I mean, where do we think this goes? It's
Yeah,
not
but nobody's
magic.
Not real waste.
Nobody's thinking that NASA engineers are playing with like fake poop and fake pee all the time. Like that's not normal.
Yeah, we would use real poo, but it's considered a biohazard on a daily basis. So really smart people came up with a recipe. And it's published.
There you go. NASA engineering, we created poop. Can you give us a verbal description here of what does the system do and kind of what does it look like in general?
I want to hear this from Jake. What's Jake's
So
take
Jake,
on it?
what does the Oscar system do?
It converts, I think the simplest way to put it converts trash to usable gas, right? Not to use that term from the older project. But we have this reactor that we inject trash into.
When you say inject, do you mean like you're like chucking trash into this?
Pretty much. So we have a reactor that doesn't have trash in it, and then we have this little separate compartment where the trash is. And when the time is right, we inject the trash into the reactor where the reactor is already preheated. It's nice and hot. So when the trash goes in there, it combusts. And then we collect all those gases from the combustion on the separate collection bottles further down.
So are you working? What kind of scale are you working on? Are you working on the scale of full size food plastics?
No, so we're cutting up. We've been burning our combusting cotton and food packaging, and what we've been doing is we've been cutting it up into 3 millimeter or 1 millimeter chunks of food packaging and cotton, and then injecting it into the reactor. So no, it's not scaled to the full size. It's just it's a miniature reactor.
Okay, so pretty small scale right now.
Correct.
Yeah, we're limited on size because we have to progressively demonstrate this concept in microgravity. So we're going to different drop towers, and the drop towers only allow you to drop something of a certain size. So if you can imagine, we're working at the shoebox size now, but eventually there would maybe be a reactor that is maybe a small trash can, like an actual trash can you'd find in your house size. So we are scaling it down just because we're confined by our test methods, but we're still able to get enough data on the concepts and the designs and the gas and the fluid flow and things like that from all the testing.
So you said this was the end of the first year of the project. Does the project have a specific lifespan, or are you just going for a goal, and when you reach the goal, the project is done?
Yeah, so the Early Career Initiative was only a 2-year project when the funding was awarded. So the project will end formally January of 2020. But something that I'm doing as the team lead is looking at future infusion of where can this go in the future? Where can this go on other NASA missions? And so there's a lot of research calls that come out. Or something that you actually helped with is, talking with industry and seeing how our work can reach back to help or take knowledge that already exists in industry and bring it back into our work. So the idea is to keep going forward with it because trash is still a problem and is not a solved solution for space travel. So yeah, Early Career Initiative will end, but this work will keep going on. I hope.
So go ahead, Jake.
No, I was just going to add that I guess the linear progression, we started out with a concept on paper. We just finished our 2-second drop tower tests. We're moving to our 5-second drop tower and then eventually a suborbital flight. And it just makes sense after the suborbital flight, eventually scale it up, get it on the ISS or even further than that.
Yeah, because this is stuff that not only are we learning for waste conversion, but even the science of solid mass, melting, thermally degrading something or combusting large amounts of mass in a controlled field. It's still a very unknown area to us. Like on Space Station, they have a combustion integration rack where they do fire experiments and flammability studies, but they're on such a small scale. So the stuff that we're doing, even though I said it was some small scale, it's still such a phenomena for so many scientists out there of combustion and how things burn or melt at the large scale in microgravity. So hopefully we can unlock some significant science for microgravity.
I remember when we were up in Glen doing our 2-second tower, we showed one of the videos of our first combustion in our reactor. We showed it to one of the doctors that have been working up there for 20 years on combustion, and his face lit up so, like, he was so surprised how bright and how big our combustion was, even though, like Andy says, it's the size of a shoebox, but still it's a bigger scale than I think he was used to.
So you mentioned Glenn, that being the Glenn Research Center. It's one of the NASA centers up there in Ohio. And so tell me about that trip. I know that you guys recently went up.
Very cold.
For us here in Florida, yes, it's chilly up there in Ohio. So tell me about that trip. You mentioned a 2-second drop tower test. Is that what you went for?
Yes. So I was so grateful because the team is so amazing. We had a minivan full of our gear and hardware, and 2 team members drove it all up and drove it back in the frigid cold. We got there. We were working pretty long hours. 5 a.m. is when the first wave of testing would happen, and we got everything set up with our payload to put everything into this chamber that was then raised about 8 stories, and then you basically drop it in free fall.
System is armed.
3, 2, 1. And then get your microgravity data, which is a whopping 2.2 seconds. Which doesn't sound like a lot, but you can get a lot of information from 2 seconds if you slow it down.
What do you need to drop things at all? Like, why is that important?
So we need to simulate the microgravity environment. So, like,
So quantify or qualify microgravity for me and for our listeners. What does that mean exactly?
I don't know how to answer that.
So here on the ground, you are experiencing gravity. Everything is pushing you down. When you drop something in free fall, you're able to simulate all of those forces acting on those bodies. They're just gone. They're just negated. So things can float, fluid and objects just behave and mix differently, and even heat transfer, the way things heat up, it just behaves so different when you don't have forces acting down on you. And that is exactly how things are in space. So on the space station, they're in microgravity, and then if you're in a planetary body, you're in some type of reduced gravity environment. So that's why it's important to do these tests in a simulated microgravity environment so we can learn, because our payload, for example, is too dangerous right now to put right on space station with a crew around it. It's too hot, there's pressure, there's a lot of oxygen, and all of that is a perfect situation for danger if you don't know what you're doing. So that's why we're trying to slowly learn by going through these incremental tests.
2 seconds. What can you really learn in 2 seconds? What was the goal and how did it go?
So I think we learned a lot in 2 seconds. Your 2 seconds may not sound like a lot, but a lot happens in 2 seconds, especially with our system, because you have to, inject the trash. You're controlling valves. You're reading pressures, and there's a lot that can happen in 2 seconds. And you're recording at high-speed video, so when you inject the trash, 2 seconds at high-speed video is a lot longer, and you can see how the trash is mixing with the oxygen, and you can see how the flame propagates inside the reactor.
What's the coming year look like? And you mentioned it's a 2-year project. You're halfway through. So what are the goals for this year?
Yeah, so Jake kind of mentioned it earlier. For year 2, we are hoping to continue on with our microgravity experiments with longer durations of time. So we did the 2 seconds. Now we're going to move on to the 5 seconds, and then we're hoping to move on to the suborbital flight of several minutes. So obviously we want hours and hours of microgravity, but we're going to do what we can to show incremental demonstration. And so it's pretty busy. We are already planning to go back to Glenn to their zero gravity facility for the 5-second testing in late February, early March. It's pretty fast. And then to potentially be on a commercial partnered vehicle demonstrating several minutes by the end of the calendar year is also a lot, especially with the hazards of our payload.
So is there a product that is the goal of this of Oscar, or is it just gathering data and furthering the process?
I'd say it is providing educational data so that we can do a proper redesign for flight hardware that will be put into space and be used by a crew. So without doing these tests, we won't really know how to properly design a reactor for microgravity. So we have to do these tests to understand so we don't mess it up.
So you talk about this getting into the hands of astronauts, which has got to be pretty exciting. Jake, have you processed like what you're doing and what this means for the future of our astronauts and humanity as we grow beyond Earth?
It's really hard to process. I think it really hit me was when one of the astronauts came and visited our lab and was looking at the work that we were doing, and he was like inspired, like, oh man, this is awesome, the work that you're doing. So a real life astronaut was looking at the work we're doing and was so proud of us, and that was an awesome feeling. And no, it still hasn't really hit me yet, but that definitely struck a chord.
So how does that look on a 6-month or more mission to Mars? That's how long, with current technology, the flight will take. So how does this system, obviously we're not there yet, we don't have it in our hands, but what's the vision for how an astronaut would actually use this system?
So that transport vehicle to get astronauts to Mars, depending on what it looks like and how big it is, our waste converter would have to be as small as possible, stay out of the crew's way, have as little crew interaction time, but it would probably be around 100 kilograms, use less than a kilowatt of power, and be about 200 liters in size. So I would say a dorm-size refrigerator.
So there's always been that balance between how much power you need to preheat the system with to eventually start creating that reaction that'll eventually produce heat and then be exothermic.
Yeah, and people don't think about it, but there's so much integration that goes on a spacecraft so that you can use energy from other parts of other pieces of hardware so that you can save on how much you need. So it's almost like the spacecraft has to be as efficient as a human body. When the human body starts overheating, you start sweating. That's just a natural phenomenon that your body does. Instead of, oh, I'm sweating, pour cold water on me immediately, or my body will shut down. Now, there are extreme cases of heat exhaustion and things like that. But for the most part, there would have to be what we call thermal management or systems engineering, where everything is talking to each other, and the vessels of the spacecraft are transferring heat from one spot or cold from another spot, and it's all going to help all of the parts on there. So yeah, you can spit out a number for one little for our specific payload right now. But when things actually get integrated and designed, you can be pulling cooling power or heating power from other things that are rejecting heat or giving off heat, and it really helps your power efficiency in the long run. So I'm hesitant to give you a final power number for the future, but
Sure.
It'll be as little as possible.
Sure.
But the trash will have to eventually get chopped up somehow and then put into the reactor to be the most efficient process. But it'll most likely be this little box that's out of your way that you don't want to smell in the capsule. Just like at home, your trash can's there. It's got to be in the middle of your kitchen, but you don't really want it in your face. So you want to get this nice little slick-looking box that you can use when you need and then get it out of your way when you're not using it. So it's probably what it would look like on a spacecraft, out of the way, latched to a wall somewhere,
Yep.
not in plain view, and just use it when you got to use it. So what would that look like? Well, we don't want the crew to spend a whole lot of time on waste conversion because they have other important things they need to be doing, like science or taking really cool pictures to send back to Earth so we can see what they're doing. But the crew would still have to somehow either feed the waste into the reactor, unless we get this really awesome response back from our challenge to help us design a good feed waste mechanism. Can I talk about that?
Oh, I was going to ask you next about that, so please do. Yeah, There's a couple of challenges going on. So thanks for bringing that up, Doctor. I'd love for you to chat about things that are ongoing for the public to get involved with.
Okay. Yeah, so right now we have this public challenge called Recycling in Space, and we're actually requesting help from the entire world. you can give us your ideas for waste receptacles, like how will an astronaut put something into a waste receptacle, but then also design the waste feed mechanism that will carry the waste from the receptacle into our hot reactor. And so we had a webinar answering questions from the audience, which is available online.
Just go to the interweb and search Recycling in Space Challenge to find out how you can participate. And keep in mind, the deadline is January 16. So get cracking.
So we're really excited because people are just coming out of the woodwork for this. And then, so it's going to take a worldwide effort to go into deep space. And so something as little as converting trash, we're going to need ideas from all over the globe. So I'm pretty excited about the challenge, pretty excited about seeing who the winners are going to be. And they have money prizes. So it's not just
For fun.
For fun. Yeah, you can win some money. So definitely check that out.
All right. Well, thank you very much. Again, I'm here with Dr. Annie Meyer and Jake Hochstadt. Appreciate you both very much. Good luck this coming year, and hopefully we'll catch up with you again and hear about your progress on year 2.
Thanks for having us.
Yeah, thank you.
I'm Joshua Santora, and that's our show. But before you go, we're going to try something new here. We would like to hear from you, our listeners. Do you have a question about space exploration? Tweet us your question at NASA Kennedy using the hashtag AskNASA, and we'll plan to answer our listener's question at the end of the next episode. Also, please be sure to subscribe to the Rocket Ranch so you never miss an episode, and tell your friends. Thanks for stopping by the Rocket Ranch, and special thanks to our guests, Dr. Ann Meyer and Jake Hochstadt. To learn more about all the cool research going on at Kennedy, go to nasa.gov/Kennedy and click Research and Technology. I'll close with a shout out to our producer, John Sackman, soundman Lauren Maythree, editor Michelle Stone, and our production manager, Amanda Griffin. And remember, on the Rocket Ranch, even the sky isn't the limit.